All right, welcome back, everybody. Today we're going to be talking about vectors. So this is the higher level only topic, and we're going to cover everything from the basic definitions of vectors, how to add vectors together. Then we're going to talk about the scalar product and how that relates to angles. We're going to talk about the vector product, how to find areas, and then we're going to talk about lines in 3D space, planes in 3D space, their intersections, angles between them, all those sorts of relationships. So with that said, let's get started. The first thing to understand is just the basic notion of a vector. So a vector you can think of as kind of being an arrow in space, okay? And the arrow as far as the IB goes can either be an arrow in 2D space or an arrow in 3D space. Okay, we're going to have both 2D and 3D vectors and nothing more than that. And when I say a 2D vector, I just mean that I can lay the vector along a piece of paper, and that's its entire direction. Whereas a 3D vector is one that I would have to point somewhere physically in 3D space. And when you have a vector that points in a certain number of dimensions, you can express each component along a particular dimension, along a particular direction. So this vector I've drawn here is a two-dimensional vector, and I can express this vertical component. I can say that that is v2 and this is v1, and then I would call the vector v1, v2, and I use this column notation to represent it. Now I can't draw a 3D vector on my piece of paper, but it's essentially going to be the same thing. You're going to have a horizontal component, a vertical component, and then you're going to have like a depth component that comes in and out of the page. And that's how you write the components of a 3D vector. So you have a v1, v2, and v3. Okay? Now, when we write 3D vectors, we have a couple of different forms that we should be familiar with. One of them relies on the fact that we have these three so-called bases vectors, I, j, and k, where I is equal to 1, 0, 0, j is equal to 0, 1, 0, and k is equal to 0, 0, 1. These are basically kind of like the coordinate axes, except that they have a fixed length. It's a direction along each coordinate axis with a length of 1. So we could say, and the choice is completely arbitrary, which one is which. We can say that this is I, that's j, and this is k, okay, forming a 3D basis like that. Now, once I've done that, I can represent my vector in column form. And remember that I said that this v1 component is the I component. And so I can write the vector alternatively as the sum of some number times the I component. So v1 times the I component plus v2 j component plus v3 k component. Now, with that understood, let's talk about position vectors versus displacement vectors. So a position vector describes the position of a point relative to a fixed origin. So we can define some point O to be the origin of our coordinate space. And then we can say that the arrow connecting O to a point P, let's say this is P, is going to be the vector OP. Okay? And it can, it can have any form, X, Y, Z. We don't really know what the coordinates are. Now, if I have points, let's say A here and B here, right? Then how do I get from A to B? Okay, that's going to be the vector AB. And the vector OA took me from O to A, and the vector from OB took me from O to B. So the way I would get from A to B is by doing what I do to get from O to A, and then doing what I did to get from O to B. So I do plus O to B. That is going to be equal to A to B. Although I'm not saying that's not exactly correct. Hang on. O to A, we have to do minus the other way. Minus OB minus OA. Yeah, sorry. I have to do a subtraction. You have to do to imagine the arrow that took me from A to B, I imagine the arrow that took me from O to B, which is OB, and then the arrow that took me from O to A, and I subtract that out, so O to A. And that is the vector AB. Okay? So these two position vectors identify points, position vectors identify points relative to the origin, and displacement vectors represent movement or translations between 2 points. So between 2 points that are not the origin, how do I get between them? So if for example, I have the position vector OB is equal to I, negative 2j, and 3k, and then OA is 2i plus j plus k, then AB would be, I do the vector for OB minus the vector for OA, and I get I minus 2I as negative I. Negative 2j minus j is negative 3j, and 3k minus k is 2k. So AB is negative I, negative 3j, and positive 2k. So in general, when we add or subtract vectors, we just add up their corresponding components. So if I have x1, y1, z1, and x2, y2, z2, and I add them up, I just have x1, x2, x1 plus x2, y1 plus y2, and z1 plus z2 in each of the components. Something similar applies for subtraction. I'm just going to subtract out each of the components. Now, addition, when you are when you add vectors together, on the plane, when you think about diagrams, it corresponds to placing arrows, the arrows for each of the vectors, head to head, and adding them up. Or sorry, head to tail, that is. So for example, if I'm doing if I have this vector OB and OA, then the vector OA plus OB is I go OB, and then I add again the arrow OA from the head of OB, and that gives me OA plus OB. Now, if I want to do OA minus OB, then I add OA and I add onto the tip of that the vector OB but flipped in the opposite direction. So I do negative OB, all right, and that gives me OA minus OB. And here's just a simple example of how you would subtract two vectors, very basic. Now, we have what is called a zero vector, which is the special vector with zero magnitude and no defined direction. So it's just 0, 0, 0. Now, you're never going to see this symbol on the IB, but it's important that you kind of know that this is how you would get from one point to another point. All right, you have a zero vector. And then the negative vector reverses the vector's direction while maintaining its magnitude. And I showed you an example over here of a negative vector, of negative OB. But basically, you just flip every component and you put a negative sign in front of them. So I have negative v is equal to negative x, negative y, and negative z. We can also take scalar multiples of vectors, and be careful, this is different from the scalar product of vectors. This is when I put some constant number k in front of a vector. Let's say it's k, then k times v is the same as putting k in front of each of the components. So kx, ky, kz. Think of that like stretching or stretching the vector either by a number greater than 1 or a number less than 1. And if k is less than 0, then the direction is going to change. It's gonna become the opposite direction because a negative number corresponds to a reflection and a scale. Now, it would be interesting to be able to think about these when we have these arrows in 3D space. How long are these arrows based on their components? And we can actually use a sort of generalization of the Pythagoras rule to say that the distance from one end to the other in 3D space is going to be, well, the distance I go over this way, and then the distance I go over this way, and then the distance I go over that way. Okay, so let's say this is V1, V2, and V3. Okay, now if you use the Pythagoras rule, you could find this distance that lies between V1 and V2, and that would be the square root of V1 squared plus V2 squared. And because this is still a right angle, then I could apply it again and square that plus V3 squared is going to give me the length. And I denote the length V. In this case, it's going to be the magnitude squared. And if you expand this, you end up with the formula that the magnitude of v, the length of a vector, is the square root of the sum of the squares of its components. And that is in your formula booklet. Let's look at an example. Let's say I'm trying to find the magnitude of the vector 1, 2, 2. Okay, I do a square root, and I do 1 squared plus 2 squared plus 2 squared is 1 plus 4 plus 4. That's the square root of 9, and that is just going to be 3. Now, let's think about this notion of parallel vectors. Two vectors are going to be parallel if one can be written as a scalar multiple of the other. So for example, if I have the vector 1, 1, 1, and 2, 2, 2, those vectors point in the same direction. One of them is just twice the length of the other, but their directions are the same. And that's what I mean by parallel vectors. I mean same direction, but not necessarily the same length. Okay, so let's look at an example here. And to be formal, you can tell that two vectors are parallel if there is some number k that I can multiply one by, some scalar that I can multiply by k. It's going to get me back the original vector. So if I let k is equal to 1/2 here, my 2, 2, 2 would become 1, 1, 1. And that essentially is telling me that I'm able to stretch the vector, one vector, to be the same as the other. And if I can stretch a vector along the direction that it's pointing and make it equal to another, those two vectors have to be parallel. So let's look at an example here. if I'm told that the vector 2ab is parallel to negative 6, 3, 9, that means there exists a k such that 2ab is equal to k times negative 6, 3, 9. And by equating the first component, I must have 2 is equal to negative 6k, and therefore k is equal to minus 1 over 3. And if I plug that back in, I find that if I do negative 1 over 3 times negative 6, 3, 9, I get 2, negative 1, 3. And that tells me that A has to be negative 1 and B has to be negative 3. Checking for questions. No, we're good. Okay, that takes us to the scalar product, which is probably the most intuitive way to multiply two vectors together. And basically, we denote it with this little dot. You're going to take two vectors and you're going to multiply each of their components. You're going to do v1, w1, v2, w2, and v3, w3. This is in your formula booklet. So as you know, let's do an example. If I have 3, 1, 2, dot product, you can say dot product or scalar product, they're the same thing. 4 minus 2 minus 1, I'm going to do 3 times 4 is 12. 1 times minus 2 is minus 2, and 2 times minus 1 is minus 2, and that's going to give me 8. Okay? Now, the dot product is going to be very, very closely connected to the angle between two vectors. All right. So if I take the scalar product of v and this v and w, that's going to give me the magnitude of v times the magnitude of w times cosine of the angle between them. And if I isolate cosine, that I can find a formula for the cosine of the angle between two vectors. And it's going to give me v1 w1 plus v2 w2 plus v3 w2 W3 divided by the product of the magnitudes. And thankfully, both of these formulas are in your booklet. Now, when I say theta is the angle between V and W, we have to be very careful because let's say this is V and that's W. Which angle am I dealing with? Am I dealing with this angle here or am I dealing with this angle here? Now, generally, the IB will tell you that you're thinking about the acute angle. They will say, let theta be the acute angle. It won't always be the case, and sometimes the angle might be negative, especially when you're doing simpler problems in 2D geometry. And it's important that you remember that the angle is measured when you put the vectors tail to tail, so between the heads of the vectors. So this angle here is between the head of one vector and the tail of the other. And you notice it's 180 minus theta and not theta. So the angle that you're going to get out is the angle between the heads of the vectors. And it's important to remember that in certain 2D geometry problems. All right? So let's do an example of finding the angle. Let's suppose that I have the vectors 1, 2, 3, and 3, 2, 1. Both vectors have the same magnitude of 1 plus 2 squared plus 3 squared. That's going to be root 14. And the scalar product is 1, 2, 3 dotted with 3, 2, 1. That gives me 10. And so cosine theta is equal to 10 over 14, or 5 over 7. And if I take the inverse cosine of that, that's going to be 44.4 degrees. Now, note that the question said acute angle, which is why I took, the calculator gave me back an angle that was less than 90 degrees. If it gives you an angle that's bigger than 90 degrees, and you want the acute angle, you have to do 180 degrees minus that angle. Now, since we have this formula for relating cosine of theta and the scalar product of two vectors, I can think about what happens when two vectors are perpendicular. And that because perpendicular means there's a 90-degree angle between the vectors, and the cosine of 90 degrees is 0. And that means that the scalar product of two vectors has to be 0, because in general, I mean, if the magnitudes are not 0. If the magnitude of a vector is 0, then there's no such thing really as the angle of between two vectors. And therefore, I can assume that neither of these are 0. But since, you know, since cosine theta is 0, I must have v dot w is equal to 0. Now, let's do an example. Let's say I have the vectors 1, 3, 2, and negative 3, 1, 3, negative 3k, 1, 3, that is, and they're perpendicular. What does that mean? It means if I take the dot product and I expand it out, I get negative 3k plus 9, because 3 and then 6. That has to be equal to 0 for perpendicular vectors, and solving that tells me that k is equal to 3. Now, again, I'm just going to remind you about the acute versus obtuse angles. If the scalar product of two vectors is negative, then cosine theta is going to be less than 0. And then just by the unit circle, if cosine theta is negative, then you're going to get an angle that's greater than 90 degrees from your calculator. But since vectors always form an acute and obtuse angle, you can always find the acute angle by subtracting 180 degrees minus theta, if theta is greater than 90 degrees. Okay, so if you ever are looking for the acute angle and you find an angle that isn't acute, you can just do 180 minus the angle that you found. So some properties of the scalar product. Unfortunately, none of these are in your formula booklet, but u c dot v is the same as v c dot u. This is not a property that will apply to the vector product later, so don't think it's always true. If I have u c dot, the sum of two vectors, let's say u dot v plus w, that's going to be u dot v plus u dot w, so I can distribute the dot product. If I have k times u dotted with v, that's the same thing as k times the dot product of u and v. And if I have u dot u, well, if I have x, y, z dotted with x, y, z, I'm going to get x squared plus y squared plus z squared. And that is the magnitude squared, because the magnitude is the square root of the sum of the squares. So u dot u is the magnitude u squared. All right, we're ready for our first problem of the day. How long is it? It's an 8-minute question. So I'm going to give you guys 5 minutes to try this on your own to get started, and then I'm going to help you solve it. All right, let's go over the solution here. So I have the vector, which is known, 7 minus 2, 3, and a perpendicular vector, v, which has components p, 4, and minus 2. Now, if vectors are perpendicular, it means that their scalar product is equal to 0. So I can say that u dot v is equal to 0. What is that scalar product? The scalar product is going to be 7p, 7 times p, then minus 2 times 4, so minus 8, then 3 times minus 2, so minus 6, that's equal to 0. So 7p minus 14 is equal to 0, means that p is equal to 2. Okay, that's my answer for part A. Now we want to find the acute angle between v and w, where w is defined as v minus u. So let's start by considering what w actually is. So w is going to be v minus u, which is going to be, let's do v is 2, 4, minus 2 now. So that's v. And I'm going to be subtracting out u, which is 7, minus 2, and 3. Okay, so I'm going to do 2 minus 7 is minus 5. 4 minus minus 2 is 6. And negative 2 minus 3 is negative 5. All right. That's pretty good. And now, let's remember that cosine of theta is going to be, well, I'm going to take the scalar product of this new vector w with v. So I'm going to do v dot w divided by the magnitude of v times the magnitude of w. Okay, so we're going to have to find each of those things before we use this formula. So the scalar product of v times w is going to be 2, 4, minus 2, dotted with negative 5, 6, and negative 5. So it's going to be negative 10 plus 24. And then negative 2 times, so that's another plus 10. So it's just going to be equal to 24. This is v c dot w. Okay, that's equal to that. And then the magnitude of v is going to be the square root of 2 squared plus 4 squared plus 2 squared. And that's going to be 4 plus 16 plus 4 is the square root of 24. And then the magnitude of w is going to be, this one's going to be a little bit bigger. We're going to have 25 plus 36 plus 25. It's 50 plus 36 is the square root of 86. All right. Now, that means now that finally cosine of theta is going to be 24 over square root of 24 square root of 86. Okay. And you can simplify that if you want as the square root of 24 over 86, square root of 86. And that makes your life a little bit easier. Now we're going to have to use our calculator. So what I'm going to do is I'm going to say that theta is equal to cos minus 1 of root of 24 over root of 86. So root of 24 over root of 86. And then I'm going to take out my calculator and check what that value is. And I'll tell you in 1 second. 24 square root divided by 86 square root. That gives me 0.528. And the inverse cos of that is apparently 58.1 degrees. Here's a harder problem. This is one of those submissions I was talking about. So I'm going to give you another I'd say 4 minutes to try this on your own because it's a pretty tricky problem, and then we're going to go over it, all right? Okay, let's go over this. So I have a parallelogram OABC, where OA is, I'm told that's going to be A, and OB is B, such that A is 3 times the length of B, okay? And I'm also told that BOA, this angle here, is pi over 3. And we want to find, in part A, an expression for OX and XA, where X is some point that lies along BC, and we're told it is such that BX is equal to K times XC. So this length here is K times longer than this length here, all right? So K is the ratio, if you will, of the length BX to XC. All right, so let's start by writing out what I know, which is that BC is going to be equal to A. To go from B to C, I just do A. I can see that on my diagram. And then I can say that BX plus XC, that's the same as BC, so that's also equal to A. And because BX is K times XC, I can say this is going to be K plus 1 XC is equal to A. And therefore that XC is equal to 1 over K plus 1A. Now that's to go from X to C, which is not exactly the expression that we want, but it helps me because now I can say that to go from O to X, I can do O to X. Let me make some room, actually. I can say that O to X is going to be O to X, we can say is going to be, I can go here, and then back here. And that's going to be B plus A minus 1 over K plus 1A. And that simplifies to B plus, from B to X, it's going to be, or can I simplify out the B? No, B plus, if I have A, that's going to be K plus 1 over K plus 1. I subtract 1, it becomes K over K plus 1A. All right, so that's my expression for OX. Now I'm looking for XA, and XA, well, I can do what I would do to go from XC, XC plus CA, which is 1 over K plus 1A minus A, okay? Or minus B, that is, minus B, my bad. So that is just going to be my answer. I do that, by the way, just visually speaking, is going from here to here, and then going from here to here. So I have my two expressions now. Those are my answers, okay? So I'm just going to make some space down here, and we're going to continue with part B, which is to find the value of K for which theta is equal to pi over 2. Now, pi over 2 is 90 degrees, and that means that I'm looking for the value of K such that OX and OA are at right angles to each other, all right? And that means that OX dotted with OA is equal to 0. And I can write that out as B plus K over K plus 1A dotted with 1 over K plus 1A minus B is equal to 0. So that's equal to 0. Now let's expand this. First thing I'm going to have is I'm going to have a 1 over K plus 1 A dotted with B. Then I'm going to have a minus B dotted with B is magnitude of B squared. Then I'm going to have a plus K over K plus 1 squared times the magnitude of A squared, A dot A. And then finally, I'm going to have a minus K over K plus 1 A dotted with B. Okay, that is a bit of a mess, but the good news is now I've used these expressions. I don't need them anymore. I can erase them at this point. All right, and therefore, I can say, well, I'm going to need to find all of these A dot B's. And A dot B, remember, A dot B is going to be magnitude of A, magnitude of B, cosine of the angle between them, which is pi over 3. And the cosine of pi over 3 is 1 over 2. So this is just going to be half of A, but the magnitude of A is 3 times the magnitude of B, so it's going to be times 3 magnitude of B squared. Okay? Now I can plug that back into this formula I have, and I'm going to end up with if I add these two terms together, I have a 1 over k plus 1 a dot b, and then a negative k over k plus 1, so I'm going to have 1 minus k over k plus 1, times what I just found, so times half times 3b squared, minus b squared, and then I'm going to have a plus k over k plus 1 squared times the magnitude of a squared, but the magnitude of a squared, magnitude of a is 3 times the magnitude of b, so the magnitude of a squared is going to be 9 magnitude of b squared, and that's all equal to 0. Now what I can do, because each term has a magnitude of b squared in it, and the magnitude of b squared I can tell is not equal to 0, I can cancel each of these out. And what am I going to be left with? I'm going to be left with 3 over 2 times 1 minus k over k plus 1 plus, and sorry, let's not forget this minus 1 here. This is going to be a minus 1. Even though I cancel it, there's still something there. Plus 9k over k plus 1 squared. And that's all equal to 0. Now we're getting pretty close to the answer because we just have this equation in terms of k. What I'm going to do is I'm going to make some room now here. And we're going to continue below. And what I'm going to do is, because I have one term, which is a fraction with a denominator of k plus 1, and another with a denominator of k plus 1 squared, I'm going to multiply everything through by k plus 1 squared. And what am I going to get? I'm going to get 3 over 2, 1 minus k plus 1, because I did k plus 1 squared over k plus 1. And then I'm going to do minus k plus 1 squared. And then this is just going to be plus 9k. And it's still all equal to 0. All right? But now I can expand all of this. And if I expand all of that, I'm going to end up with, and to make my life even easier, I'm going to multiply by 2. So instead of 3 over 2, I'm just going to have 3. And then I'm going to have minus 2 of these and plus 18k there. It's going to make things a little bit easier. Now I have 1 minus k times 1 plus k. That's actually a difference of squares. So I'm going to have 3 times 1 minus k squared. Or I'll actually just write that as 3 minus 3k squared. And then I'm going to have minus 2 times k plus 1 squared, and k plus 1 squared is k squared plus 2k plus 1, so I'm going to have minus 2k squared minus 4k minus 2 plus 18k is equal to 0. All right, so now let's collect everything I have. Now I have negative 5k squared. Then I have negative 4k plus 18k. That's going to be minus 14k. And then finally I have 3 minus 2 is 1, so plus 1 is equal to 0. Now, this is a quadratic that I can solve. All right, I'm going to rewrite it over here, make the leading term positive just because it makes me less likely to make a mistake, but you don't have to do this if you don't want to. And I'm going to have that 5k squared plus 14k minus 1 is equal to 0, and therefore that k is equal to negative 14 plus or minus the square root of 14 squared minus 4 times 5 times minus 1, all of that divided by 10, 2 times 5, okay? And I don't want to square the 14 because otherwise it's going to be a bit messy, but I'm going to realize that I have 14 is 2 times 7 squared, and then I have so I have 4 times 7 squared, minus 4 times 5 times minus 1. I can factor the 4 out of the square root as minus 14 plus or minus 2 root of 7 squared plus 5, right? And then if I divide that out, divide that, 7 squared plus 5 is going to be 49 plus 5. That is going to be 54, and 54 is 9 times 6, so I can actually factor out a 3 again, and then I'm going to have equal to minus 14 plus or minus 6 times the root of 6, all over 10. And I can simplify that one last time to be negative 7 plus or minus 3 root 6 over 5. Now, The question says find the value, so there might be two, but you have to be very, very careful here to realize that if I have minus, if I was doing minus, is it supposed to be minus? No, it's supposed to be a positive 7. So what did I do wrong? Hang on. Sorry, this was plus 14k. This was minus 14k. I made a sign error. And this is plus 14 plus 14 plus. Okay, so it's 7 plus or minus 3 root 6. But 3 root 6 is greater than 7 because the root of 6 is bigger than 2.5. And therefore, if I do 3 times root 6, it's going to be bigger than 7. And so 7 minus 3 root 6 would be less than 0. So I have to reject 7 minus 3 root 6 because it's less than 0. And so I must only have k is equal to 7 plus 3 root 6 over 5. That is my final answer. Okay, another hard problem. I'm going to give you a 5-minute head start, and then I'm going to catch up behind you. All right, so we have a regular hexagon A, B, C, D, E, F. Regular meaning that all of its sides have the same length, okay? And AB is equal to U, and BC is equal to V. Now, the point X lies somewhere along the diagonal FC, such that XC is equal to 3f of x. Not f of x, 3fx. And we want to show in part A that the 3 points A, X, and E are collinear, meaning that they lie along a straight line. Now, what do I know? First of all, I know that AE is going to be, I can go to AE by doing V, V, and minus U. So AE is equal to 2V minus U. Okay, that's the first step. Now I'd like to have an expression for AX. Okay, now I can say that AX is equal to AF plus FX, right? Plus FX. And I know that this length here is 3 times the length of this one, which means that the entire diagonal is 4 times the length of fx. So FC is equal to 4 times fx, right? This little piece here is 1/4 of the diagonal. And if it's 1/4 of the diagonal, then I can find an expression for FC relatively easily. FC is going to be just 2u for fx. And so fx is going to be equal to half of u. All right, so that's fx. And therefore ax is going to be af, and af I can say is v minus u. So v minus u plus half of u is v minus half of u. Okay? Now, I can say that AE, I notice that AE is twice AX. If I take this and I double it, I get that above. And that means that the points A, X, and E are collinear because this vector here is parallel to the vector that goes through all of them, and so they have to lie on the same straight line, okay? So A, X, E are collinear, right? And that's part A. Let's just remember one thing, which was that fx was equal to half of u. Half of u. Now, in part B, it says that using a vector method, we are to find the exact value of cos of bxa. And bxa, if I draw it here, is going to be this angle here. All right, that angle there, bxa. Now, to use a vector method to find the angle, I'm going to have to do something like, I'm going to have to consider bx dotted with ax. Okay, I'm going to have to consider that scalar product. And let's remember that ax was equal to v minus u plus half of u was v minus half of u. V minus half of u. And that now I can say that bx is going to be, well, I can do something similar. I can do bx is going to be ax, but then, so like bx is going to be b to a plus a to x, and b to a is minus u, so it's, and then minus u plus v minus half of u is going to be v minus 3/2 of u. Okay? Now, if I were to try and find the magnitude of ax, hang on, the magnitude of ax is going to be this dot product with itself, ax dot product with itself, square root. So it's going to be the square root of the magnitude of v squared minus magnitude of u, magnitude of v, plus a quarter of the magnitude of u squared. So I did v minus half of u dot product with v minus half of u, because the dot product with itself gives me the square of the magnitude. Okay? And I took the square root of that. Now, I know that both v and u have a magnitude of, sorry, and there's actually a small mistake in there. I forgot the cos of the angle. Okay, so when I take the dot product with itself, let me write it down below so there's a bit of extra space. I can say that ax squared is going to be v squared minus u v times cosine of the angle between them. So that's 120 degrees, cosine of 120 degrees, plus a quarter of u squared. Okay? Now, that's going to give me, the cosine of 120 is going to be negative 1 over 2. So this is going to be, since v squared is going to be 1, right? Both side lengths have a length of 1. So I'm going to have 1 minus 1 over 2 plus 1 over 4. That's just going to be 3 over 4. All right, that's the length ax. And now the length bx, well, bx, if I square that, if I take the dot product of this with itself, I'm going to get the magnitude of v squared minus v times 3 over 2u, that times 2, because there's a cross product term. There's a, it's like a plus b squared. So I have a squared plus 2ab plus b squared. So I'm going to have minus 2 times v times 3 over 2u. So minus 3 v u cosine of 120 degrees plus 9 over 4 u squared. That's going to simplify to 1 minus 3 over 2, because cosine of 120 degrees is 1 over 2, plus 9 over 4. If I put everything over 4, that's going to give me 4 over 4 minus 6 over 4 plus 3 over 4. So that's going to be 1 plus 3 over 4. That's going to be 7 over 4. Okay? 7 over 4. Double check that. Is that true? Yeah, 7 over 4. Okay, so that is some useful information. Let me write it down over here. The magnitude of ax is 3 over 4. The magnitude of bx, and I should say squared, but let's just do a square root, is equal to square root of 7 over 4. And now I need to make some room over here, and we're going to consider the scalar product of bx and ax. So I found that ax was equal to v minus half of u. Remember, we found that in part A. And by considering that bx was ba plus ax, I said that bx was going to be v minus 3/2 of u. And so if I finish erasing this, what am I going to get? I'm going to find that bx times ax is going to be, well, I can do v minus half of u dotted with v minus 3/2 of u, just to write out an extra step. That's going to be equal to v squared, then minus 3 over 2 v u cosine of 120 degrees, then minus 1 over 2 u v cosine of 120 degrees, and then plus 3 over 4 u squared. So 3 over 4 u squared. Now, the side lengths are 1, so this is just 1 minus 3 over 2 minus 1 over 2 plus 3 over 4. All right, and that should give me, when I take those together, I should just get, and I think Did I maybe say something wrong? Hang on. Oh, it's not 3 over 2. It's 3 over 4 here. My bad. This is 3 over 4. And this is 1 over 4 because I forgot the cosine of 120 was half. So 1 over 4. Okay. So this just simplifies to 3 over 4. Nice. And now that I know that, I'm going to come up here and we're going to say that the cosine of the angle between these two, cosine of the angle BXA is equal to that scalar product, so 3 over 4 divided by the product of the magnitudes. So it's going to be the square root of 3 over 4 times the square root of 7 over 4. So square root of 3 over 4, square root of 7 over 4. Okay. That is going to give me equal to the 4's are going to be in the denominator because they're going to multiply together. And the square root is supposed to be over the entire 7 over 4. So that's my bad. So square root of 7 over 4. That means in the denominator, I'm going to have the square root of 21 over 4. So I'm going to have 3 over 4 over the square root of 21 over 4. And that's going to simplify to 3 over root of 21. And you can rationalize the denominator if you want to, but you don't have to do that. Okay, that was tricky, but we found that angle. All right? Okay. In part C, we are told that BM squared, so there's some point that lies along the diagonal FC, such that BM, this distance here squared, plus MD, which is that distance squared, is equal to this distance squared. Now, when do I have the square plus a square equal to another square? That's when I have a right angle triangle. And that tells me that I have a right angle here at M, so that BM dot MD is equal to 0, okay? And I can set up an expression for M in terms of some unknown, parameter K. So I can say that CM is going to be K times CF. So it's K is going to be between 0 and 1. It's some part of the way along the diagonal. So K is greater than or equal to 0, less than or equal to 1. So that it lies on the diagonal. And if that's what CM is, then I can find an expression for BM. And remember that CF itself, let's actually do one more step. CF is equal to negative 2u. So this is negative 2ku. All right. And now I can say that BM is going to be BC plus BM. And BC is V. So I'm going to have V minus 2ku. All right. That is for BM. And now for DM, I can say I do DC. Okay, so DC, I'm going to go from here to here, and then I'm going to add the same thing. So DC is just going to be, well, I can do U minus V. So it's going to be, now I'm talking about DM is equal to U minus V minus 2ku. So that simplifies to 1 minus 2ku minus V. All right, perfect. Now I can write what I know, which is that V minus 2ku times 1 minus 2ku minus V is equal to 0. And I can expand that. I'm going to have 1 minus 2k, and then the magnitude, so V dot W, just from now on, we're going to do a shortcut. Anytime I have V dot U, let's remember that V dot U is going to be the magnitude of V, magnitude of U, times the cosine of 120 degrees. All right, cosine of 120 degrees. And since the side lengths are both 1, I'm going to have 1 times 1 times a half, just a half. So I'm just going to remember that as a shortcut. It's going to make my life easier. So this is going to give me 1 minus 2k times 1 half. And then the next term is going to be just minus v squared. So minus v squared. And that's going to be 1. We'll simplify that in a second. And now I'm going to have minus 2k times 1 minus 2k. 1 minus 2k u squared. And finally, plus 2k times u dot v, which we said was 1 half. equals to 0. Let's expand everything that I have here. I'm going to have 1 minus 2k times a half minus 1 minus 2k times 1 minus 2k plus k is equal to 0. And we're almost there now. I can say, I'm going to multiply both sides by 2. It's going to be a little bit easier. I have 1 minus 2k minus 2, then minus 4k plus, now it's going to be plus, it would have been 4k squared. Now it's going to be 8k squared because I multiplied by 2. So plus 8k squared plus 2k is equal to 0. All right. Now I've got to turn this into a quadratic. I'm going to do that. I can write it down here. There's still enough room. So I'm going to have 8k squared. And then I'm going to have minus 2k minus 4k plus 2k. So that's just going to be minus 4k minus 4k. And then I'm going to have, for my constants, I'm just going to have 1 minus 2. That's going to be minus 1 is equal to 0. Okay. Perfect. Now we are getting pretty close. So what I'm going to do is I'm going to make some room up here so that we can continue solving this. All right, and now I solve this quadratic. All right, so I'm going to say that k is going to be equal to 4 plus or minus the square root of b squared is going to be 16. And then minus 4 times 1 4 times 8 times minus 1 is going to be plus 32. All right, that's all being divided by 16. 16. This is going to be 4 plus or minus the square root of 48. And the square root of 48, I can factor out, that's 3 times 16, so plus or minus 4 root of 3 over 16. Now remember that k we said had to be between 0 and 1 because it lies, the point M lies along the diagonal. So I can't have 4 minus root 3, that would be negative. So I take the positive case, and I say I have 4. If I now, divide 4 out of the numerator and denominator, I get 1 plus root 3 over 4. So that's the value of k. We're not 100% done yet, though, because we need to find the distance between these 2 points here. Okay? So let me just erase and make a bit more space. What I'm going to do is I'm going to write a similar expression to what I wrote for CM for CX, and we're going to just see how far apart they are. All right. So I can say that now I have CM is equal to negative 2KU, and therefore I can say that MX is, so how do I go from M to X? So I can go from M to C, and then from C to X, right? From C to X. All right, so this is going to be 2KU because I flipped the sign of that for MC. I'm going backwards. And then CX is 3/4 of the diagonal, so it's plus 3/4, and the diagonal is negative 2U. Negative 2U. All right. And so if I simplify that as much as I can and factor out the U's, because U has a length of 1, so actually the length is going to make no difference, and so I can say that the length, if I factor out the U, I'm going to have U times 2k, and then minus 3 over 4 times 2 is 3 over 2. Okay, and so my length is going to be, the magnitude of mx is going to be 2k minus 3 over 2, which is equal to 1 plus root 3 over 2 minus 3 over 2. Oh, well, yes, that's fine, because basically the direction I have mx is going to be negative. That's okay. I have to put absolute value around this, so that's okay. So absolute value of 1 plus root 3 minus 3 over 2 is going to be root 3 minus 2 over 2, okay? And root 3 minus 2, well, root 3 is smaller than 2, so it's going to be the other way around. It's going to be 2 minus root 3 over 2, or in other words, 1 minus root 3 over 2. That's my final answer. We've talked about the scalar product. Now it's time to talk about the vector product, right? And the vector product is definitely a bit more complicated of an expression, but it's in your formula booklet. And we define the vector product of v and w to be this complicated sort of combination of different components, all right? what I want you to notice is that in the first row of the cross product, we take the product of the second and third rows of the uh, two vectors that we are cross producting, and there's no v1 or w1 up here, all right? And then in the second row, where there's no v2 or w2, and in the third row, there's no v3 or w3, all right? Now, I'm not going to go over where this formula came from, but this formula uh, is essentially a guaranteed way of producing a vector that is going to be perpendicular to both v and to w. So now we're dealing in 3D space. So if I have a vector v, like this, and a vector w like this, then this new vector is going to be sticking out so that it's, at a right angle there, a right angle, and a right angle in 3D space. Okay? Now it's going to be perpendicular to both of the original vectors, and technically speaking, you're supposed to know about this like right-hand rule, which is that if you point your index finger in the direction of v and your middle finger in the direction of w, then your thumb is going to point in the direction of the cross product. But in IB, we've never cared about the direction of the cross product, so I'm not really sure you need to know that. But here's an example. If I have negative 2, 1, 3, vector product with minus 1 to minus 3, that's going to be, in the first row here, I do 1 times minus 3, minus 3 times 2. All right, that's the first row. In the second row, I do 3 times minus 1, minus negative 2 times negative 3. And then in the third row, I do negative 2 times 2, minus 1 times minus 1. And if I do all that arithmetic, and it's a procedure where it's very, very easy to make mistakes, so you should be super careful when you're doing this, you will get negative 9, negative 9, 2. All right? Let's continue. So some properties of the vector product. One thing is that if I switch the order of u cross v to v cross u, I don't get the same cross product. I get the negative of what I had before. So the order actually matters here to some extent. Similarly, if I have u crossed with v plus w, that's going to be u cross w plus u cross w. So the vector product still does expand across brackets. And same thing for scalar multiples. If I have ku vector product with v, it's going to be k times the vector product of u and v. Also the same thing as u times the u vector product with kv, same thing. And also I have u crossed with u, the vector product of any vector with itself is going to be 0. All right? Because, you can think about this. Remember, the vector product gives me a vector that's perpendicular to the two vectors that I gave it. But there's actually, if I just have one direction, there's an infinite number of vectors that are going to be perpendicular to it. And so the cross product in some way doesn't know which vector to return. And so it sort of just has to be 0. And you can see that it's going to be 0 just by sort of plugging into the formula as well. All right. Now, u cross v is equal to 0 means that u and v are parallel for any uv that are non-zero. All right. So that's another interesting property, and it's actually it's the general case of this u crossed with itself being 0. If it gives me 0, it's because the two vectors are parallel. Okay. Now, there's a pretty important relationship between the vector cross product and the areas of parallelograms. And it's important not just for finding the areas of parallelograms, but also because it reveals a lot about how the vector cross product works and how we can interpret it. So I want you to imagine this parallelogram, and a parallelogram means that I have uh, basically two sides that have that are parallel to each other. So this is parallel to that, and that is parallel to that, and the opposite sides have the same length as well, okay? That's a consequence of them being parallel. So those are parallel. And let's say that this is V and this is W. The area of this parallelogram in 3D space, if V and W are vectors, is going to be V crossed with W, okay? That's going to be the area of the parallelogram. That's in your formula booklet. Now, what I want you to think about is what we kind of know from trigonometry is that if this angle is theta, then the area of the triangle we said is half, it'd be half the length of V times the length of W times the sine of theta, right? This is just the sine rule for area. And so the area of the parallelogram would be VW sine of theta, okay? Which means that since that is supposed to be equal to v cross of w, the magnitude of v cross of w, then I can say that sine of the angle between two vectors is going to be v cross w over v w. Okay, so if I take the magnitude of the cross product divided by the product of the magnitudes of each of the original vectors, I get sine of the angle between the two things. And in particular, you notice that when the angle between the two things is 0, that means that the cross product has to be 0, which is what I was saying here. If the cross product is 0, it's because two vectors are parallel. Okay? And you notice, therefore, that the cross product is going to have a maximum magnitude when theta is equal to 90 degrees. That makes sine theta be equal to 1. And so that's when the vectors are perpendicular to each other. All right? Now, the reason I'm, zooming in on this point is because there are going to be problems later where we talk about the distances to a vector or distance to a plane. And it's very, very useful to use the cross product in some of those cases, and in some cases to use the scalar product. But I want you to think about the vector product a little bit as, let's say I have a vector here and I have a vector here, okay? If I take the scalar product of these two, it's basically actually going to tell me what the length is if I project one of these onto the other. If I were to kind of take the shadow of one of the vectors onto the other, what would that length be, right? So this would be, if this is u and v, this would be u dot v, and the vector product is going to do something similar, but kind of actually the opposite. It's going to tell you, it's hard to draw what this represents. It's going to tell you how much of the length of u lies in the direction that is not parallel to v, okay? And that sounds a little bit weird if I say it like that. I'm going to see if I can maybe express it a bit differently. It's kind of like the scalar product of u with a vector v tells you how much v lies in the how much u lies in the direction of v, and the vector product tells you how much it lies not in the direction of v. Okay, so it's kind of like isolating the component that lies along a particular direction and the component that lies not along a particular direction. And that might feel a little bit confusing now. It'll make more sense later when we talk about examples of distances. Yeah, so this is what I was saying. There's a connection between the product and the sine, and therefore, I mean, this is in your formula booklet, we can find the sine of the angle using the vector product. All right? So, time for another problem. I'm going to give you 5 minutes to do this, and then we'll keep going. Okay, let's go over this. So we are trying to prove in part A that the magnitude squared of u cross v plus the magnitude squared of the scalar product is equal to the product of the square magnitudes of the two vectors. So let's start by using the fact that u crossed with v is equal to u v sine of theta. This is in your formula booklet. And also that the magnitude of, or that u dot v is equal to u v cosine of theta. And therefore that the magnitude squared of u times v, u cross v squared plus the square of u dot v is equal to u squared v squared. The first one is going to be sin squared theta plus cos squared theta, and that is going to be equal to just u squared v squared using the Pythagorean identity. Okay, sin squared plus cos squared is equal to 1. Now, in part B, we want to use the identity found in A to find the value of sine 2 theta for two particular vectors. So we're told that the obtuse triangle, so obtuse meaning that I have, let's see, I have a triangle that looks something like this. I can say that this is OA, that's OB, okay, and the area of the area here is 2. And that OA, I mean, let's just say that this is A and B, so I can say A dotted with B is minus 3. and we'll say that this is the angle theta. Okay, so what do I know? I know that the area is going to be half the magnitude of A cross B. Okay, that's one thing I know. A cross B. And if I know that A dot B is equal to 3, it means that A B times cosine of theta is equal to -3. All right, that's what I know. And now what I can do is I can think about, because the identity that I have involves U cross V squared, right? So the area here is equal to 2. What I'm going to do is I'm going to square both sides, and I'm going to say that 1 over 4 A cross B squared is equal to 4. Or in other words, A cross B squared is equal to 16. All right. Now, what does that mean? It means that if I did that squared, so if I did, I can also say, yeah, so if I did A cross B squared plus A dot B squared, I should get the product of the magnitudes. I should just get A squared B squared, okay? A squared B squared. But now I know that this is 16, and I know that A dot B is -3, so this is 9. So this is going to be 25 is equal to A squared B squared, okay? So that is one thing, and that tells me that the product of the magnitudes A, B is just equal to 5, if I square root both sides. All right? Now I can go back to this formula and say that cos of theta is going to be -3 over 5, because this is equal to 5. And if cos theta is -3 over 5, then I can say that sine theta, well, sine theta is going to be 1 minus cos squared of theta, so 1 minus 9 over 25. This is sin squared, is going to be 16 over 25. And so sine of theta is going to be equal to 4 over 5. Because theta is an obtuse angle, it's still less than 180 degrees, because an angle in a triangle has to be less than 180 degrees, and so sine is going to be positive. So sine theta is 4 over 5. And finally, I use this identity that sine of 2 theta is equal to 2 sine of theta cos of theta, and that is going to be 2 times 4 over 5 times -3 over 5, so 2 times 4 times -3 over 25. That's -24 over 25. That is my answer. We're now ready to talk about vector lines. Okay, so far we've been talking about vectors between two specific points, whereas a vector line is defined by a fixed point and a direction vector. So basically, vector lines continue infinitely. And to have a vector line, you have to know one point on the line, and then you have to know the direction the line is going in. All right? And the most common way to represent the lines is in the so-called vector form, where I give you the coordinates of a point, you have the direction vector, and then you just put this unknown lambda in front of it, and that means basically that I can take any point on the line, I can take the point on the line, and add any multiple of the direction vector, and I'm going to get to somewhere else on the line, right? Just by adding multiples of the direction vector. So that's what that equation is telling me. So here's an example. Let's find the equation of the line passing through 1, 0, 1 that's parallel to -1, 2, 3. It's very simple. I take the point 1, 0, 1, and I add any multiple, lambda, of -1, 2, 3, and that is my equation. All right, so the equations themselves are not too difficult. It's what we do with them that's going to be a little bit trickier. So let's continue to the second form of the line, which is just nothing more than taking the form that I had before and saying, well, let's say x, y, z is going to be equal to, well, what do I have? Let's say I have, I have some point on the line plus lambda times, let's say, a direction L, M, N, right? So this is the formula that's in your booklet. We turn it into we break up the x and the y and the z separately. We say it's x0 plus lambda L, y is equal to y0 plus lambda m, and z is equal to z0 plus lambda n. Now, this is particularly useful when you're trying to solve for the intersections of lines. You're basically just breaking it up into specific equations that you can use to solve a system. All right? Now, I think the hardest form is the so-called Cartesian form of a straight line. And I want you to think about the Cartesian form as sort of like the Cartesian form of a straight line in 2D, if you remember how that works, which is where I take a specific point. This time it's in 3D, so x naught, y naught, and z naught. And I'm going to imagine that any other point on the line, if I take the difference of those two, so if I did x minus x naught, y minus y naught, and z minus z naught, that's going to be, this vector here. Well, that vector has to lie along a particular direction, and that direction is LMN. LMN. Okay? Which means that if I were to take x minus x naught and divide it by L, how much I'm supposed to go over in the x direction, that should be equal to y minus y naught over m, the amount of change in y divided by how much the y is supposed to change in this direction, and that should also be equal to z minus z naught over n. Okay? So when I put these side by side, you get this formula that's in your formula booklet, and it basically emphasizes the consistent ratio of coordinate changes along the line. And if either one of these direction vectors is going to, if any of the component of the direction vector is 0, then that coordinate does not change. So if I have a direction of, let's say, 1 or 2, 1, 0, then that direction vector does not change. So I have to have an equation. I have to equate the first two components that do change, and the third component is just going to be constant. All right. Now, that hasn't shown up in the IB, but it could. All right. So here's an example. If I have the line x minus 3 over 2 is equal to y plus 4, and z equals 2, let's write that in vector form. So z is not changing. Z is just 2. So I'm going to have 2 plus lambda times 0, because it's not going to change. And then I'm going to have the point 3 and minus 4 on the line. So 3 minus 4 I can put there. And x is going to change twice as fast as y because there's a 2 in the denominator. So I have 2, 1, and 0. All right. Let's continue. One of the most common problems that shows up on the IB when it comes to vectors is using vectors to model simple kinematics, which is motion in 3 dimensions. And you can use a vector line, and instead of having a parameter lambda, we often use a parameter t to represent time. And then what happens is the direction vector, if I call it, b, the vector b, that's going to represent the velocity of the object, right? The direction that it's changing and also the size of that direction. And if I take the magnitude of b, that is going to give me the speed, okay? The rate at which it moves, irrespective of the direction, all right? So we're going to do an example now. I'm going to give you 5 minutes to get a head start, and then we're going to talk about this together. All right, so first of all, we're told that in this question, distance is measured in feet. So let's remember that because it's going to be important when we are writing down our answers. And now we're told that Anna and Michael are flying toy helicopters in straight lines at constant speed. And the position of Anna's helicopter, t seconds after it passes through A, is given by 3, 1, minus 1, plus t times the direction to 1, 2, 3. And we want to find, first of all, the speed of Anna's helicopter. And the speed is going to be the magnitude of 1, 2, 3. Magnitude of the velocity, that is going to be the square root of 1 squared plus 2 squared plus 3 squared. That's the magnitude of, well, it's going to be 1 plus 4 is 5 plus 9 is 14, so root 14 feet per second. Okay, that's why it's important that we remember that it's in feet. Now, after 5 seconds, Anna's helicopter passes through point B. And first we want to find the coordinates of B. So B is going to be equal to 3, 1, minus 1 plus 5 times 1, 2, 3. Okay, that's going to give me 3 plus 5 is going to be 8. 1 plus 5 times 2 is going to be 11. And negative 1 plus 5 times 3 is going to be 14. So those are the coordinates of B. That is 8, 11, 14. Okay, so here was root 14. Here we found 8, 11, 14. All right. Now, next step. We want to find the distance AB. So I know that A is the original point the helicopter started at, because it says that the position is given by ... where The position is t seconds after it passes through A. So it passes through A when t is equal to 0, and that means that A is just going to be 3, 1, minus 1. So A is equal to 3, 1, minus 1. But it doesn't actually matter because all the displacement AB is just going to be 5 times the direction. 1, 2, 3. Okay? And so that's just going to be 5, 10, 15. Okay? And now that distance, if I take the distance AB, first thing I'm going to do is I'm going to factor out 5. And I'm going to now put the square root of 1 squared plus 2 squared plus 3 squared. It's the same again. It's going to be 5 root 14. I probably could have been smarter about that and just said the distance is going to be 5 times the speed, right? 5 times root 14. Okay, so this is 5 root 14. I could have been smarter about that. But anyways, now we're told that Michael's helicopter travels in a direction 4, minus 1, 2. And the two helicopters collide at A. And we want to find the value of R. That's the first thing we want to do. Okay, so find the value of A, that is, when the point at which the two helicopters collide. So let's set up an expression. Basically, if I know that they collide at A, I don't even need the direction of Michael's helicopter yet. I can just say that 3, 1, minus 1 plus t times 1, 2, 3 is equal to A. And therefore 3 plus t is equal to A. 1 plus 2t is equal to A. That's already enough equations, but I'll write down the last one. Negative 1 plus 3t is also equal to A. And I have all three of these equations. Okay, now what I can do is I can say, why don't I take, this is equation 1 and equation 2. I'll do 2 times equation 1. Sorry, I'll do 2 times equation 1 minus equation 2. And that's going to give me 6 plus 2t minus 1 plus 2t is equal to 2a minus a. So in other words, it's going to give me 5 is equal to a. And therefore a is equal to 5. So a is equal to 5. All right. And that means that when the time at which that happens is going to be, so 3 plus t is equal to 5. And that means that t is equal to 2. So 2 seconds after Anna's helicopter passes through A, they were going to collide, okay? So when t is equal to 0 is 2 seconds previous. So where was Michael's helicopter 2 seconds previous? So if it was at 5, 5, 5, when it passed through its initial point, let's say x, y, z, and then it did plus 2, because we found t is equal to 2 times 4 minus 1, 2. All right, so I can solve, I can say x is going to be equal to 5 minus 2 times 4, which is equal to negative 3. Y is going to be 5 minus 2 times minus 1, which is going to be equal to 7. And z is going to be equal to 5 minus 2 times 2. That's going to be equal to 1. So negative 371 is going to be my answer. So negative 371 is my answer. Now we're going to talk about intersections of lines. And this is, I think, where vectors gets very tricky. Intersections of lines and then planes and intersections of planes. So we say that two vector lines intersect if they share exactly one common point. And in particular, that means they are not parallel. If they were parallel, they would have an intersection. In fact, they would have infinitely many intersections, but they wouldn't be intersecting. We say they're just, so we can separate out the case of coincident lines, which we'll talk about in a sec. We say that intersecting lines are not parallel. So for example, consider the lines 1, 2, 3 plus lambda 4 times 4, 0, 0, and then 2, 1, 1 plus mu times 3, 1, 2. If I set them equal, it leads me to the system 1 plus 4 lambda is equal to 2 plus 3 mu, 2 is equal to 1 plus mu, and 3 is equal to 1 plus 2 mu. Now, if I solve that system, if I solve, these two equations, if I subtract 3 minus 2, that's going to give me just mu. That tells me that mu is equal to 1, okay? And that leads me to lambda is equal to 1. And substituting that back in, it shows that I have a unique point of intersection, 5, 2, 3. Now, there are going to be some systems of equations that you set up between two lines that are going to have no solutions. You'll find that, for example, maybe these two equations together give you one solution, but that solution doesn't work for the remaining two equations. And that's when you can tell that two lines don't intersect. Sometimes you're going to have systems of equations that have seemingly too many solutions. It seems like no matter what you pick, you're going to have essentially free choice for one of the variables. And that means that your two lines are actually the same line, okay? Not just intersecting, but the same line. That leads us to the angles between lines in 3D space. We already know what the angle between two vectors is. And now if I imagine that I have two infinite lines in 3D space, it's relatively easy to understand why the angle between them is just going to be the angle between the two direction vectors, okay? Because the direction is what determines how the lines are actually pointing. I don't really care about specific points on the lines. If the lines are going to intersect, I don't really care about the specific points, okay? So here's an example. Let's find the acute angle between the lines x minus 5 over 3 equals y plus 2 over 2 equals z plus 1, and 1, 3, negative 5 plus lambda 3, 1, 2. So the direction vector of this line, x minus 5 over 2 plus y plus 2 over 2 is equal to z plus 1, is, I don't know why it says 3. This is supposed to be a 3. 3, 2, 1. This is 3, 2, 1. Okay? And both direction vectors have the same magnitude of 14. And so theta, cos theta, is going to be the dot product of 3, 2, 1, dotted with 3, 1, 2. That's going to be 9 plus 4 is 13, and their magnitude multiplied together is going to be 14. So cos theta is going to be 13 over 14. If you use your calculator, you will find the acute angle of 21.8 degrees. Two lines are parallel if their direction vectors are scalar multiples of each other, and the lines are not coincident. So the lines are, the direction vectors are the same, direction vectors are parallel, but they also don't share a point. If they shared a point, they would be coincident, okay? And that's what makes lines parallel. Now, another case of the intersection of two lines is coincident lines, which means they represent exactly the same line. So every point on one line also lies on the other. Now, for lines given by r1 is equal to a1 plus lambda b1 and r2 is equal to a2 plus mu b2, the lines are coincident if the direction vectors are parallel. So one of the vectors, the direction vectors are scalar multiples of each other, and one point on one line also lies on the other, because if two lines, if two lines share a point, right, they share that common point, and they have the same direction vector, then they're going to share all their other points as well. So it's enough to show, if you're trying to show that two things are coincident, that there is one point in common, and that the vectors are parallel. That's enough to show that the lines are coincident. So here's an example. I have two vectors given by r1 is equal to 1, 2, 3 plus lambda times 2, 4, 6. And I have a second vector, 3, 6, 9 plus mu times 1, 2, 3. So these lines are coincident because their direction vectors are parallel. This one is double this one. So the lines are parallel. And this point, 3, 6, 9, lies on this line. If I let lambda equals to 2, I get 3, 6, 9. So this point lies on both lines, and therefore these two lines are coincident. The last case of lines are what we call skew lines. And this is actually isn't the last case. There's one more case. But we have, in general, the most common case, if you randomly picked lines, is for them to be skew, okay? And that means that they're going to be neither parallel nor intersecting. And you can see what that looks like in this diagram. They just kind of miss each other, right? They pass, they come relatively close together, some distance apart, but they just continue, and that's it, all right? Nothing else happens. So let's consider when that would happen. So if the direction vectors are not scalar multiples of each other, then the lines are not parallel. And then when you try and set them equal to each other, you will find that there's no solution. I was mentioning this earlier. Okay, so if you set them equal to each other and you try and solve, for example, this system with this example, you'll find, for example, that from the, if you equate the components, 1 plus lambda is equal to 2 mu, 2 plus lambda is equal to 1 plus mu, 3 plus 3 lambda is equal to 0. This last equation tells you that lambda is equal to -1. And if I substitute that into the first equation, that means that mu must be equal to 0. But that doesn't work in the second equation, right? Those two don't work. And so you're actually going to find that there's no choice of lambda and mu that can satisfy all three equations, all right? And that tells me that there is no intersection. And it's the fact that they're also not parallel that tells me that these lines are askew. If the directions were parallel and there's no intersection, then they would just be parallel lines. All right. That is everything from lines. We're going to talk about planes now, okay? So A plane in 3D space can be described by a vector equation involving a fixed point and two direction vectors lying in the plane. So I want you to imagine this plane here, this sheet, right? It's spinning around, we can see it. And I've drawn in this plane two lines that lie completely flat in that plane. All right? And I want you to imagine that I can get to any point on this plane by moving some distance along the first line and then some distance in the direction of the second line. So it's kind of like, imagine that this green plane here is a little bit like the coordinate plane that you have in 2D, and we know that two axes, two directions, is enough to actually get anywhere on the coordinate plane. I can go some direction in the x direction and some direction in the y. But those directions don't actually need to be perpendicular. It's possible, for example, I can say that I get from here to that point by doing, this much in this direction and this much in that direction. Okay, perfectly valid way of thinking about how you get to somewhere in the plane, even if you don't have two lines that are perpendicular. They still are going to be what we call a basis for this plane. All right. So the most common equation for a plane then is to write, okay, let's say r is a point in the plane, can be expressed as some point that I know to be in the plane, then some multiple of the first line in the plane, and another multiple of another line in the plane that's not parallel to the first one. Okay, and that is going to define a plane. Okay, I can go some distance along this line and then some distance along there. That gives me a plane. Okay, so we can do a little example here. Let's find the vector equation of the plane that passes through the points A, 1, 2, 3, B, 2, 1, 4, and C, 3, 2, 1. First, let's find the point from A to B and A to C. If I do B minus A, I get 1 minus 1, 1, and C minus A gives me 2, 0, minus 2. Those are not parallel, so those are going to work. And I can say that my vector equation of the plane is going to be the point A, so 1, 2, 3, plus lambda times the direction AB, so lambda 1 minus 1, 1, plus mu times the direction AC, so 2, 0, minus 2. It's perfectly valid. Now, in general, that form is very, very difficult to handle because now you have this nasty equation that has two parameters, lambda and mu in it. It has two different direction vectors and a point. It's actually very difficult to work with. The most efficient form that we have for thinking about planes is what we call the normal form. And the reason that the normal form is so useful is that we remember that if I take, these two lines that are in the plane, if I take the cross product, the vector product of those two lines, I'm going to get a line that is going to be perpendicular to both of them. And in general, if you have a flat sheet, like a plane in 3D space, there's only one direction, or technically two, because it can be the opposite direction, that's going to be pointing directly away from the plane. So what we say is we can represent the plane as nothing more than one point in the plane, plus the direction that is perpendicular to the plane. Because if we know the direction perpendicular to the plane, we know which directions are going to be parallel to the plane or lying in the plane. And there's going to be, infinitely many choices that I could make for exactly which lines lie in the plane. But I want you to imagine this little diagram here. I've drawn that arrow there, which represents the normal. And you can see a point in the plane that's moving around such that the angle between this point at the base of the plane and the arrow is always at a right angle to the point from the base of the plane to the point in the plane. Okay, so it's always going to be a right angle there. And why is that useful? Well, let's say I define the normal to be the vector product of any two direction vectors in the plane. So B crossed with C, all right? And it's not a unique normal because I could go in the other direction or I could multiply it by 2 or whatever. It doesn't really matter. Direction vectors in general, there can be infinitely many directions parallel to this normal, but any one will do. And sometimes you'll be asked to think about a unit one, which means a length of 1, but that's sort of a separate question. So here's an example. Let's say I have the plane pi, which has the equation 1, 2, 3, plus lambda times 1 minus 1, 1, and mu times 2, 0, minus 2. It's the example from the previous slide. So the direction vectors here are 1, minus 1, 1, and 2, 0, minus 2. That means that the cross product of these two vectors is going to be 1, minus 1, 1, and 2, 0, minus 2. All right? If I actually do the vector product of those two things, I'm going to get 2, 4, 2. And that's parallel to 1, 2, 1, and I'd rather simplify into that form, so I'm just going to say 1, 2, 1. All right? Now, if 1, 2, 1 is the perpendicular vector, the normal vector to the plane, I can take the point 1, 2, 3, which I know is in the plane because it's here. So 1, 2, 3 is in the plane, and I can say that A if I take A dotted with my normal vector, I get 8, all right? And that means that any point in the plane is going to have to satisfy R when I take the dot product with 1, 2, 1 is going to be equal to 8. And let me maybe explain why that formula holds, okay? So I want you to imagine that any point in the plane, right? In the plane, I have the points R, which are A plus lambda B plus mu C. And if I take the dot product of that with n, I'm going to get A times n plus lambda b c dot n plus mu c dot n. But b and c are direction vectors in the plane, and we defined n to be b cross c, so that n was perpendicular to b and perpendicular to c, which means that b dot n is equal to 0 and c dot n is equal to 0. And so this simplifies to just a dot n. All right, and a dot n is a number that I can calculate, and I found in this case that it was 8. So that's why this formula works. It's the special choice of n that means that when I take the dot product of this equation with n, it simplifies down to this really nice, elegant form of just, some vector, some point that lies in the plane, dot product with my normal vector gives me some constant number. And it's a much, much simpler form to deal with than the previous form that we talked about. Now, there's a very closely related form to the normal form that we just talked about, which is the general form or the Cartesian form of a plane. And if you note that we have r dot n is equal to a dot n, where a is some specific point in the plane and r is an arbitrary point in the plane, then let's call a dot n the constant d, all right? And if we say that r is x, y, z, and n is a, b, c, some direction, then I can write ax plus by plus cz is equal to d when I actually take the scalar product, okay? And it's a form that you're going to see a lot on the IB, and it's a very clean form for representing planes. So if a plane has an equation r dot 1, 2, 1 is equal to 8, again, the example from the previous slide, then if I let r be equal to x, y, z, then I get x plus 2y plus z is equal to 8. And that is going to be the general or Cartesian equation for the plane. Now, one of the big advantages of this form is it makes it a lot easier to think about the intersections of planes, okay? And we're going to talk about that in a second, but we're going to have systems of multiple planes, ax plus by plus cz is equal to d, and then some other line, let's say x plus 2y minus z is equal to 4. So you're going to have these systems of equations of planes that you're going to be able to solve a lot more easily in the general form than in any of the other forms. All right, let's go over the solution here. So I'm trying to find the point Q on the plane pi with the equation given that is closest to the point 4, 5, minus 3, and to find that shortest distance, okay? So the first thing I'm going to do is I'm going to note that the two direction vectors are 6, 2, minus 3, and 3, 2, minus 2, which means the normal vector is going to be the vector product of those two things, so 6, 2, minus 3, crossed with 3, 2, minus 2. Okay, and that is going to give me, if I write it out one by one, it's going to give me minus 4 plus 6, minus 9 plus 12, and 12 minus 6. Okay, and that, if I simplify, is going to be equal to 2, 3, 6. Now, why am I finding the normal vector to the plane? Let me draw a little picture here. My plane, I can say, looks something like this. And obviously, a plane goes on forever, but you have to draw the boundary somewhere so you can see it. And this is my point P. Sorry, that's the point P. This is the point Q on the plane that is closest. And I realize that the point is going to be closest when this forms a right angle to the plane, right? So it's like the closest distance is a perpendicular distance to the plane. So how am I going to find that that distance and that position Q? First, I need to find the normal because I know, therefore, that then QP is going to be some multiple of the normal vector. And it's going to be useful to find n hat, which is the unit normal vector. So what I'm going to do is I'm going to do 1 over the magnitude of n times n. And the magnitude of n is square root of 2 squared plus 3 squared plus 6 squared is going to be 4 plus 9 plus 36 gives me 49. So it's going to actually be 1 over 7 times 236. That is my unit vector. And it's going to be a little bit more useful because now I have a vector that has a length of 1 that lies that is normal to the plane. Okay, so that's useful. Now what I can do is I can say, well, let's take any point on the plane, all right? Let's say that I take the point, why not take 3, 1, minus 2? Because I have that point 3 minus 1 minus 2. So 3, 3 minus 1 minus 2. All right, and draw that there, okay? And that's going to be the distance RP. So let's find what RP is going to be equal to. So RP is going to be P minus R. So that's going to be 4 minus 3, 5 minus minus 1, and minus 3 minus 2. All right, that's going to be equal to 1, 6, and minus 1. Okay? Now, here is the trick that I want you guys to really understand for all of these distance questions. The easiest thing when you have the distance to a plane, and there are different ways to do this. The most effective way to think about this is to use the scalar product of some arbitrary distance to this normal vector. So if I note that this angle here is theta, then the distance I'm looking for is the adjacent length, and this distance here is the hypotenuse length. Or in other words, the distance if I have cos of theta, cosine theta is equal to a over h. And so I can isolate a is equal to the adjacent distance I'm looking for is just going to be h cosine of theta. Okay, and cosine of theta, h cosine of theta, cosine of theta is related to the vector product, right? So h cosine of theta is going to be equal to, well, RP dotted with RQ divided by the magnitude RP magnitude of RQ, all right, specifically. And RP is just, the magnitude of RP is just 8, so this is going to simplify to RP dot RQ over RQ, all right? Now I'm setting up like the intuition behind this formula, but in general, what you can do is you can take any length, any vector from the plane to the point, and just take the scalar product with the normalized or the unit normal vector, okay? And that is going to tell me how much of the vector that I have, RP, lies along the direction from P to Q. And the reason that I made it a normal vector was so that when I take the scalar product, I'm not actually going to be stretching the vector that I have. So let me show you what that would give. I'm going to have my vector RP dotted with the normal vector. Okay, and that should give me, because the normal vector has a magnitude of 1, it should give me, and these are supposed to be, yeah, so that should give me the magnitude of RP times the magnitude of n, which is just 1, divided by, sorry, not divided by, that times cosine theta. So it should give me the magnitude RP times 1 times cosine of theta, all right? And RP times the cosine of theta is going to be this length times the cosine of theta, so the hypotenuse times the cosine of theta, which is going to give me the adjacent length. And so this does indeed give me the correct answer. And so if I actually evaluate that, if I do RP dotted with that, I'm going to get 1 over 7 times 2 times 1, so 2, and it's no longer a vector, sorry, now it's a scalar product, so 2 times 1 is 2, 3 times 6 is 18, and 6 times minus 1 is minus 6, okay? So that's going to give me 1 over 7 times 2 plus 18 minus 6, and that gives me 1 over 7 times 14 is 2. So that is the distance, all right? Now, how do I actually find the specific point Q on the plane? Well, if I know that this distance is 2, I can go from P, and I can go a distance 2 in the direction opposite the normal that I found. All right, so the normal that I found was this, and that's a unit normal, so it has a length of 1. So if I do P minus 2 times that unit normal, I'm going to get the point that I want. So let's do that. Let's do P, we are told in the question has the coordinates 4, 5, minus 3. So I can do 4, 5, minus 3, and say Q is going to have the coordinates of p minus 2n, okay? And technically you should put OQ for vectors, but no p, whatever. And that's going to be 4, 5, and minus 3 minus 2 times the normal vector, which is 1 over 7 times 2, 3, 6, okay? Now, the final answer is not going to be super, super pretty because I have this 1 over 7, but that's okay. Can put everything over 7, and I can say that the x component is going to be 28 over 7 minus 2 times 1 times 2, so minus 4 over 7, so 24 over 7 is the first component. Then that 5 becomes 35 over 7, minus 2 times 3 is minus 6 over 7, so I'm going to get 29 over 7. And then finally, I'm going to have minus 3 is negative 21 over 7, minus 12 over 7, so that's going to be negative 33 over 7. And that is the point P, okay? So you can put it also in coordinate form, 24 over 7, 29 over 7, minus 33 over 7. Both are fine, okay? I'm going to check for questions because that was tricky. If there are any questions, feel free to put them in the Q&A. We do have a bit of time to go over it if you'd like to. This method for using the normal vector to a plane, finding its magnitude so that you can find a unit normal, and thinking about the scalar product is the best way to do distance from a plane. There are other ways, but this is by far the most effective way to do it, okay? So I think you'll be better off in the exams if you understand this method and can do it. Now we can talk about the intersection of a line and a plane. Well, if I have a plane that looks something like this, and a line that goes somewhere in space, they're going to intersect, in general at one particular point. Now, the line could lie in the plane, that's possible, but in general, there's just going to be one intersection. And we can find it by taking the equation of let's say I have the plane 1, 2, 1. So this is a line. 1, 2, 1 plus lambda times 2 minus 1, 3. And the plane x plus y minus z is equal to 3. If I plug in each of the x, y, and z from the Cartesian form, or from the parametric form of this line, I get 1 plus 2 lambda plus 2 minus lambda minus 1 plus 3 lambda should be equal to 3. And that simplifies to lambda is equal to minus 1 over 2. If I plug that into R, I find the intersection 0, 2.5, and minus 0.5. We can also think about the angle between a line and the plane. So imagine I have, as you see in this picture, a plane and a line with a direction vector of d. And it forms this angle of phi with the plane. What you can do is you can think about the angle that phi is going to form first with the normal, because the normal vector, if I have the normal vector, I know how to find the angle between two vectors. So that would give me the acute angle theta. And then phi is just going to be 90 degrees minus that because it lies in this right angle triangle like you see in the picture. Okay? And therefore, here's a little example. If I have the line 0, 0, 0 plus lambda 2, 3, 1, and the plane with normal 3, 1, 4, then the direction vector of the line is 2, 3, 1. So the angle between d and n satisfies cos theta is equal to d dot n over magnitude d times magnitude n. That's going to be 13 over root 14 times root 26. If I use my calculator, I'll find an angle of 47.05. And that means that phi, the angle between the line and the plane, is 90 degrees minus that is going to be 43 degrees. Now we can talk about the intersection of two planes. Notice in this picture, I have two planes that are intersecting. Unless those two planes are parallel, then the intersection is going to be a line, right? If I take two kind of sheets that extend forever, they're going to intersect along a straight line, okay? And basically that straight line is the direction vector that they have in common. So what does that mean? It means that we can find the intersection by solving a system of equations. Like I said, it's easiest to do this when you have the vectors in Cartesian or general form. So let's say I have the planes x plus 2y plus 3z is equal to 4, and 2x minus y plus z is equal to 3. And because I have two equations and three unknowns, I know that I'm going to have what we call 1 degree of freedom, which means that I have one more variable than I have equations, and so I have to start by saying that one of the variables is going to be arbitrary. I know that it's not going to lead to one specific solution. So I start by saying z is equal to t, okay? And from the second equation, that means that y is going to be equal to 2x minus 3 minus t, because z is equal to t, okay? And that means then, and also in the first equation, I can say x plus 2y is equal to 4 minus 3t. Now, if I substitute that expression for y into the first equation, that gives me x plus, some mess. And simplifying that down tells me that x is going to be equal to 2 minus t. And because y was equal to 2x minus 3 minus t, I substitute that back in, and I find y is equal to 1 minus t. So now I have these three things. I have z is equal to t, I have x is equal to 2 minus t, and y is equal to 1 minus t. So what do? I make, first of all, the 2 the point on the line. I make 1 also the point on the line, and because there's 0 here, I make 0 a point on the line. And then I let the direction vector be whatever is multiplying the t's in each of the equations. So in the case of x, it's minus 1. In the case of y, it's minus 1. And in the case of z, it's just 1. Okay? And that's how I would find the equation of the intersection. We can also find the angle between two planes using the same trick with the normals. Let's say I have these two planes that are intersecting to form an angle of theta. Well, let's draw their two normals, okay? And the normals are going to intersect to also form an angle of theta. We just have to be careful to make sure that if we're looking for the acute angle between the planes, that we actually find the acute angle between the normals. So if you get an obtuse angle, just make sure to do 180 degrees minus that angle to find the acute angle. Here's an example. I have the planes 2x plus y minus z is equal to 6, and 2x minus y plus z is equal to 2. That means the normal vectors are 2, 1, minus 1, and 2, minus 1, 1, both of which have a magnitude of square root 6. So I can say that cosine of theta is going to be the dot product of the two, so 2 times 2 plus 1 times minus 1 plus minus 1 times 1, divided by root 6 times root 6, the product of the magnitudes. And that simplifies to 1 over 3. That means that theta is going to be the inverse cosine of 1 over 3, which is 70.5 degrees. I have the two planes, x plus ky plus z is equal to 4, and kx plus y minus z is equal to minus 6, okay? And I'm told that k is bigger than 1 over 2, and theta is the acute angle between the planes. And we want to show in part A that cos of theta is 2k minus 1 over k squared plus 2. So let's identify the two normals of the planes. I have the normal 1k and 1 by looking at the coefficients of x, y, and z in the first equation. And I have the second normal, k1 minus 1. Okay? So I can say that cosine of theta is going to be the dot product of n1 and n2 divided by the magnitude of n1 times the magnitude of n2. All right? What is that going to give me? That's going to give me k plus k minus 1 over the magnitude of n1 is going to be the square root of k squared plus 2. And this is going to be also, for the second normal, k squared plus 2. And so that simplifies to 2k minus 1 over k squared plus 2. Now, the question says that theta is an acute angle, but that's no problem because we're told that k is greater than a half. So this is always going to be positive, which means that theta is going to be an obtuse angle, no matter what the value of k is here. So that is part A. Now in part B, we're trying to find the minimum possible value of k, of theta. Okay, so remember that cosine theta on the unit circle represents the horizontal position, it represents the horizontal position of a point that forms an angle theta with the x-axis. So let's say that this is the point. This is going to be theta, and this is going to be the cosine of theta. So the angle is going to be smallest, minimum, when cosine of theta is at a maximum, because it's going to be, let's say that's the maximum value of x. That's going to be a smaller angle of theta. So we're looking for the minimum, the maximum of cosine theta. And we know that cosine theta is 2k minus 1 over k squared plus 2. So let's just say that I'll just say f of k is equal to 2k minus 1 over k squared plus 2. Well, how do I find a maximum? I find f prime of k, and I set it equal to 0. What is the derivative going to be? Well, the derivative is going to be, I can take u equals to 2k minus 1, and v equals to k squared plus 2, so that u prime is equal to 2 and v prime is equal to 2k. And then according to the quotient rule, f prime of k is going to be u prime v minus v prime u over v squared. That's going to be 2k squared plus 4 minus 4k squared plus 2k, or minus 2k, okay, like that. And that's going to simplify to, well, we'll simplify in a second. First, let's do the denominator. V squared is going to be k squared plus 2 squared. All right, so let's expand that. The numerator now becomes negative 2k squared plus 2k plus 4 over k squared plus 2 squared. And that's supposed to be equal to 0. And it's going to be equal to 0 when the numerator is 0. So in other words, k squared minus k, or plus, minus k minus 2 is equal to 0. I factored out minus 2 from the numerator. And this is going to happen when I can say this gives me k, what is it? K minus 2 times k plus 1 is equal to 0. So I have the roots k is equal to 2 and k is equal to 1, but it's only k is equal to 2 since I have k greater than a half. So k is equal to 2. All right. Now, that doesn't actually tell me what the angle is yet. It just tells me what the value of k is. That tells me if I plug that into here that I'm going to get 2 times 2 minus 1 is 3 over, and k squared is now going to be 4 plus 2 is 6. So cos theta is going to be 1 over 2. And cos theta is 1 over 2 when theta is equal to 60 degrees. So that is the minimum possible value of theta. Now, let's talk about the intersections of 3 planes. We talked about the intersection of 2 planes forming a line, and the intersection of 3 planes can form multiple different cases. I can have sometimes 3 planes intersecting at a point. That's this case here. 3 planes intersecting at a point. Okay. I can have 3 planes intersecting along a line, right? If the intersection of one pair of planes is the same line as the intersection between a second pair of planes, okay? And the case where the 3 planes don't intersect anywhere. Now, if you remember that the intersection of 2 planes is always a line, then if I have 3 planes, then think about, the equation, the intersection of pi 1 and pi 2. Let's say that that gives me L1, and the intersection of pi 2, or pi 1 and pi 3 gives me L3 or L2. Then those 2 lines, in general, they can either be parallel lines. That's the case where the planes don't intersect anywhere. They can be skew. That would also mean they don't intersect anywhere. Or they could be intersecting lines, and that would give me a point intersection. Now, sometimes if the lines are coincident, then I'm going to get 3 intersections. That's this case. I'm gonna get a line of intersection. That's this case here. Okay. So the intersections of the planes and the cases they form are actually, in a way, just the cases of the different ways that lines can intersect amongst themselves. All right. So we're trying to show that L1 is the intersection of pi 1 and pi 2. And the easiest way to do that is to show that L1 lies in both of the planes. So let's turn this equation of the line into a more convenient vector form. So let's say I'm going to do 3x over negative 12. I both have a common factor of 3, so I can say I have x minus 5 over 3 over negative 4 this time. And then I'm going to have y plus 2 over 3 if I factor out the 3 from the numerator and denominator, and that's all equal to z over 3. In other words, this line is 5 over 3, negative 2 over 3, 0, plus lambda times the direction minus 4, 1, and 3. Okay? If I take the point 5 over 3 and I plug it into the equation for pi 1, I get 5 over 3 minus 2 over 3 plus 0, and that does equal to 1. And so pi 1 is satisfied, and that means that this point lies in the plane. All right, so pi 1 is satisfied. 5 over 3, negative 2 over 3, 0 lies in pi 1. If I plug it into pi 2, I get 5 over 3, or 2 times that, minus negative 2 over 3 plus 3 times 0. That's going to give me 10 over 3. Plus 2 over 3 is going to give me 12 over 3. That's going to be 12 over 3, which is equal to 4. And so pi 2 is also satisfied. All right. Now, the planes have normal vectors 1, 1, 1, 1, 1, 1, and n2 is equal to 2, minus 1, 3. If I take the scalar product of 1, 1, 1 with minus 4, 1, 3, I get 0. And if I do the same thing for 1, 1, 1, sorry, for 2, negative 1, 3, excuse me, 2, negative 1, 3, and for minus 4, 1, 3, I also get 0, which means that the direction is perpendicular to both lines. So 4, minus 4, 1, 3 is perpendicular to n1 and n2, okay? And so it lies in both planes, because a line that is perpendicular to a normal means that it is parallel to the plane. So it's parallel to both planes, it lies in both planes, and therefore L1 does indeed have this equation here, okay? Now in part B, we're trying to show that if I have a third plane, kx plus y plus 2z is equal to 3, and L2 is the intersection of pi 3 and pi 1, then L2 has the equation r is equal to 0 minus 1, 2 plus lambda times 1 k minus 2, 1 minus k. Okay, so what I'm going to do is I'm going to set up the equation x plus y plus z is equal to 1. That's the first plane equation. And the second one, I've got to turn into normal form. So it's normal is going to be actually no, we're given the equation of the plane. What am I saying? So and the second equation is going to be kx plus y plus 2z is equal to 3. And I'm going to try and solve this equation simultaneously. So I'm going to start by subtracting the first equation, or the first equation from the second. So I'm going to do kx plus y plus 2z minus x plus y plus z. That should give me 3 minus 1, or 2. So, all right, so I'm going to have k minus 1 x. My y's are going to cancel. I'm going to have plus z is equal to 2. All right, that's already helpful. And that therefore I can say that z is going to be 2 minus k minus 1 x. Or equivalently, I can say 2 plus 1 minus k x. All right. Now, given that x plus y plus z is equal to 1, I can plug in what I know for z, and I can say, or I can actually say more easily, that y is going to be equal to 1 minus x minus z, which is equal to 1 minus x minus 2 plus 1 minus k x. And that is going to be equal to 1 minus, I have minus 1x minus another 1 minus kx. So that's going to be minus 2 minus k x, and then I'm going to have minus 2. Okay, so minus 2. And that simplifies to y is equal to k minus 2 x minus 1. Okay? Now, if I say x is equal to lambda, because I have lambda in this equation, then I can say that y is going to be k minus 2 lambda minus 1, and z is going to be 2 plus 1 minus k lambda. And that leads me to the equation r is equal to 0, 1, and 2, where the 1, and sorry, minus 1 and 2, plus lambda times the direction that I found, which is 1, k minus 2, 1 minus k. All right? And so we've showed that indeed L2 has that equation. Now, in part C, we are considering the case where L1 and L2 are parallel, and we have to find the value of k. So the lines are going to be parallel if, remember that earlier we found the direction vector, minus 4, 1, 3. That's supposed to be now parallel to 1, k minus 2, 1, 1 minus k. All right, now I can tell by looking at minus 4 and 1 that I have to have minus 4 over 1 is equal to 1 over k minus 2. And therefore, cross multiplying, I must have 8 minus 4k is equal to 1. and therefore 4k is equal to 7. K is equal to 7 over 4. All right, so that's my answer for k. I'm going to write that down here. K is equal to 7 over 4. Let's check it off. 7 over 4. All right. Now, in part D, I'm trying to find the shortest distance between the two lines in this case. Okay, so what do I know? I know that now L1 and L2 are parallel for this value of k. And so the shortest distance, if I draw these two lines, the shortest distance is going to be a perpendicular line between the two. So it's going to be something like that. All right. And so that if I let A be a point on L1 and B be a point on L2, then I can say that, in fact, let me do any point. I still know that the shortest distance is going to be a perpendicular, but it's more useful to consider an arbitrary point and show you why the formula I'm going to give you works. All right, so this is L1 with the point A on it, and this is L2 with the point B on it, okay? And let's say that I have this distance here, and the shortest distance is still going to be the perpendicular here, like this, all right? Now, let's say that this angle here is going to be theta, okay? Then the distance that I'm looking for, if I find the distance AB, that represents the hypotenuse of a triangle, and I'm looking for the opposite side. Or in other words, I can say that sine of theta is equal to opposite over hypotenuse, and since I'm looking for the opposite, I can just say that I'm looking for opposite is equal to AB sine of theta, okay? Sine of theta. And the useful trick for finding these distances between parallel lines, I showed you one earlier for the distance to the plane with the scalar product. This second one is to remember that sine of theta is related to the cross product. I can say it's V cross W magnitude over magnitude of V magnitude of W. That's in your formula booklet. And so in the case of AB and L2, which has direction, in this case, with k is equal to 7 over 4, I have 1. 7 over 4 minus 2 is negative 1 over 4, negative 1 over 4, and negative 3 over 4. That's the direction. Then I can say that the length that I'm looking for is AB sine of theta, which means that the distance I can write is going to be AB crossed with V divided by the magnitude of V. And that's going to work because this is going to give me, if I did AB cross of V over V, that is going to give me, if I take this formula, I can say that V cross W over V is equal to W sine of theta. And that's what I'm looking for. I'm looking for this W sine of theta. I'm just saying W is equal to AB, okay? And V, we can say, is the direction of L2. And but you know what we said? The direction of L2 is parallel to L1, and we know that L1 has a direction of minus 4, 1, and 3, so minus 4, 1, 3. And so I can take actually this cross product and then find its magnitude, and divide that by the magnitude of V alone. So let's actually do that. And you're going to find, if I do that, I'm going to find AB crossed with W with V is going to be, well, AB, I have to set up, we got to pick 2 points on the plane, so I may as well pick A is equal to 5 over 3 minus 2 over 3 and 0, because that one obviously lies on the plane. It's the one we found earlier. And I may as well say B is equal to 0 minus 1, 2. So that AB is equal to minus 5 over 3, minus 1 over 3, minus 1 over 3, and 2. And then if I take the cross product, I'm going to have minus 5 over 3, minus 5 over 3, minus 1 over 3, 2, crossed with V, which is minus 4, 1, 3. Now, I'm going to make some space now that we kind of have this formula understood, so we have the room that we need to find the answer. I'm going to have to take this vector product and then find the magnitude. So let's take the vector product. And it's going to be, first of all, I'm going to have minus 1 over 3 times 3 minus 2 times 1. That's the first row. And then I'm going to have 2 times minus 4 minus 5 over 3 times 3. And then I'm going to have minus 5 over 3 times 1 minus, times 3, not times 1, times, no, it's times 1, it's times 1. And then minus 1 over 3 times minus 4. Minus 4. Okay, that simplifies down to, I have minus 1 over 3 times 3 is minus 1. Minus 2, that gives me minus 3. Then I'm going to have negative 8 minus 5 over 3 times 3 is going to be negative 5 over negative 5. So I have minus 8 minus 5. So plus 5, so I have minus 3 again. And then I have minus 5 over 3 minus, here I have minus 1 over 3 times minus 4. So I have negative 5 over 3 minus negative minus 4 over 3. So that's going to be negative 9 over 3 is also negative 3. Okay, so that is my vector product. And it's going to have a magnitude. So that means the magnitude of AB cross V is going to be equal to, I can factor out the 3. I can say it's going to be 3, and then the square root of 1 squared plus 1 squared plus 1 squared is going to be root of 3. And finally, the magnitude of V is going to be equal to the square root of 4 squared plus 1 plus 3 squared, and that's going to give me root of 26. All right, and so I can say, therefore, that the distance is, do I have any room to write here? The distance is going to be AB cross V over magnitude of V, and that is going to give me 3 root 3 over root of 26. That's my answer. So we found, well, K already was 7 over 4. We found that, and this was 3 root 3 over 26. Let's just check off that answer. 3 root 3 over 26. Over root 26, that is. And now we are considering the case where L1 and L2 intersect to form an acute angle of theta. All right, so I have L1, L2 intersecting and forming an acute angle of theta. So the direction vectors of the two lines are, one of them has minus 4, 1, and 3, and the other has direction vector 1, k minus 2, 1 minus k. So the angle between the two, cos of theta, is going to be the scalar product of the two. So I'm going to write minus 4, 1, 3. In the sake of space, I'm not writing them vertically, so I save a bit of space. 1, k minus 2, 1 minus k. And all of that is going to be divided by the product of the magnitudes. And I already know that the magnitude of minus 4, 1, 3 is root of 26. I found that in the last part. And then the magnitude of the one in terms of k is going to be 1 plus k minus 2 squared plus 1 minus k squared. All right, now let's do the numerator. It's going to be minus 4 plus k minus 2 plus 3 minus 3k. And all of that is going to be divided by root of 26 times the root of, if I expand all out, I'm going to have 1 plus, so let me write it, 1 plus k squared plus 2k plus, or plus 4k, that is, or minus 4k, plus 4, and then plus 1 minus 2k plus k squared. It's getting a little bit messy, but that's going to simplify down to, I'm going to have in the numerator, I'm going to have k minus 3k is minus 2k, and then minus 4 minus 2 is minus 6, plus 3 is minus 3, all divided by square root of 26 times the square root of, and it does indeed simplify to 2k squared minus 6k plus 6. All right, just gathering the terms that I have. All right, so that answers part E. We have shown, oh, we're just missing the absolute value. Why is there an absolute value around cos theta? let's say cos theta, and I'm going to say as theta is acute, we add absolute value, because if cos theta is acute, then cosine has to be greater than 0. So we add absolute value. All right. Make sure you write exactly why you have to add the absolute value, or you're going to lose a point for not explaining why there's an absolute value. And finally, in the last part, we're trying to find the possible values of k for which theta is equal to 60 degrees. So if theta is equal to 60 degrees, it means that cosine of theta is 1 over 2. So I have 1 over 2 is equal to minus 2k minus 3 over the root of 26 times the root of 2k squared minus 6k plus 6. Okay? If I square both sides, I'm going to get 1 over 4. And if I square the absolute value, they're going to be positive anyway, so I can just write minus 2k minus 3 squared. And it's going to be divided by 26 times 2k squared minus 6k plus 6. Now what I'm going to do is I'm going to cross multiply. I'm going to bring the 26, 2k squared, etc. to the left-hand side. And 26 over 4 is going to be 13 over 2. And that's going to be times 2k squared minus 6k plus 6 is equal to, and now if I expand my 2k minus 3 squared, I'm going to have, well, because there's a negative on the inside, and I'm going to square the whole thing, it's going to be the same thing as 2k plus 3 squared, so I'm going to have 4k squared, then plus 12k plus 9, okay? And now what I can do is I can realize that this 2 is going to cancel with each of the 2's in all of the terms there, and I'm going to end up with 13k squared minus 39k plus 39 is equal to 4k squared plus 12k plus 9. Now, if I simplify that, I get 9k squared minus 51k plus 30. Okay, and I said something slightly wrong. I must have. Hang on, there's a mistake here. 4k squared plus 12k plus 9. Oh, no, it's fine. Minus 51k plus 30 is equal to 0. Now I can divide everything by 3, and I get 3k squared minus 17k plus 10 is equal to 0. Now I can factor this by inspection. I'm looking for 3 times 10 is 30, and 30 is minus 15 minus 2, so that works perfectly. 3k squared minus 2k minus 15k plus 10 is equal to 0. So in other words, I'm going to have k times 3k minus 2 minus 5 times 3k minus 2 is equal to 0. So I get k minus 5 times 3k minus 2 is equal to 0. So my answers are k is equal to 5 or k is equal to 3 over 2, or 2 over 3, sorry, 2 over 3. Okay. That was really difficult. That was the hardest vector question I could come up with. I wanted to do something hard. And I know that that distance formula is not necessarily officially on the syllabus or such, but there have been questions on the IB as recently as 2021 where there are other ways of doing it, but it's much, much easier if you know that formula. It's just the most effective way to solve these questions. So I would recommend you know how to do so. All right? That's the end of the vectors session. I hope that was clear and productive. I recommend you go and do more problems on the website because there's a lot more intricacies that we haven't necessarily covered 100% of. Yeah, good luck. Good luck studying.